In this lesson, we're going to be talking about exponential functions and then the property of equality right after we talk about those. So this graph here is an exponential function. If we are looking for an exponential function, what we mean by that is that we have a variable in the exponent. We've had graphs before like this, y equals x squared. That's a quadratic function where it makes a parabola, where the x is the base and the 2 is the exponent. What's different about an exponential function is that the 2 is the base and our variable is the exponent. So when we have an x or a variable of any kind in our exponent, that's when we have an exponential function. So what we want to look at is the domain and range of this. I'm looking right now, if I was going to take a vertical line, let me go ahead and draw one in here. If I'm looking at this vertical line and I'm tracing it, and I'm tracing it across my graph. Notice here how this looks like it continues on this line. So I'd be touching at negative infinity, and then it would appear to go on forever. So my domain would be all reals. You could either say, depending on which notation you were talking, interval notation, we'd say negative infinity to positive infinity, or in set notation, values of x such that x belongs to all reals. My range then, if I was going to flip this, and I'm going to do my horizontal, it doesn't look like I'm touching anywhere below the 0, right? Doesn't it kind of look like this right here is an asymptote? That's going to get closer and closer to that line but never touch. So I'm going to say I start touching after 0 and then I touch forever. So I would say that my range is from 0, and I'm going to make that a parenthesis because I don't think it's touching at 0. I think that looks like a horizontal asymptote, all the way to positive infinity. That's interval notation. For set notation, I'd say values of y such that y is greater than 0. From what I'm looking at there, that's what it looks like, right? The one thing that we'd write in here in our little box is as the value of x decreases, the value of y approaches 0. What that means is, I'm going to actually start my graph right to left here. As I'm going here, my x is decreasing, isn't it? As I'm going across, those x's are getting less than and less than. So x is becoming more negative. So I'm decreasing, and as I'm decreasing, these values start to approach y is what it's called. And so, the values of y are approaching 0. So see how my range was 0. Those values are approaching 0, meaning they approach it but don't ever touch it. That's an example of the graph. This example here is an example of exponential growth. The other one we're going to talk about is exponential decay. So when you look at those, here's the two graphs you have on your notes. When we have exponential growth, that's for examples where our base is greater than 1, meaning problems like the one we just did. My base is 2, so since it's greater than 1, my graph made an exponential growth problem. If my base is between 0 and 1, I have exponential decay. So an example of that would be y equals 0.5 to the x. That's a value between 0 and 1, and I have exponential decay then, meaning it's going. You'll notice as my x values get bigger, my y values are approaching 0. So that's going in the opposite direction. And we're going to do some word problems eventually with this, so you'll see how exponential growth and exponential decay are used. If you are going to be a science major of any kind, you will do lots of work with exponential growth and decay actually, and you probably have already used logs, possibly in science classes junior year. So when I look here, you will notice though that my base is never 0, so it can't equal 0, and my base is not negative. So I don't have any negative bases or a base of 0 here, so that's something you should observe. As we keep going here then, just to name these on the bottom as growth or decay, remember that if it's greater than 1, it's growth, and if it's less between 0 and 1, it's decay. So our first one is 1/5. Hopefully you realize that's between 0 and 1, so we'd say that's decay. Our second one is the number 4, which is greater than 1, so we would say growth. And then my third one is 3/2, which is 1.5, which is greater than 1. So we have growth. So just recognizing, so these graphs, you could picture them. This one's going to go down like this one's going to go like this one's going to go like this. Somehow like that. I mean, that's a very rough sketch. But you at least know the direction of the graph from looking at the base. Then you'll see on the bottom, we have on the bottom of the notes on your first page, it says property of equality, b to the x equals b to the y. When the bases are the same, then x equals y. So for letter A, take a look at the back of your notes. That's where we're going to start doing those problems. For letter A, these are our bases. When our bases are the same, The property of equality tells me that I can set the exponents equal and they'll be the same also. So when I do that, I would get x to equal 5. And if you want to check your answer, you could say 3 to the 2 times 5 equals 3 to the 10th, which does check that 3 to the 10th equals 3 to the 10th. So we're looking to solve for x here. So take a look at B. Bases are the same, so I set my exponents equal. So when I add 10 to both sides, I'd have 3x equals 60, and I'd get x to be 20. So those aren't too bad, right? We can see that the bases are the same. Those are pretty easy to solve. If you take a look at C, you'll notice this is the first one where my bases aren't the same. So my goal is to try to make the bases be the same. Now remember, my bases are 3 and 9. So is there any way I could turn one of those numbers into the same base? You want to think of like squareds and cubes here. I know that 9 is the same as 3 squared. So I'm going to keep my 3 to the 2x the same, but I'm going to replace that 9 with 3 squared, and then it'd be to the 10th power. I'm not changing the value of this number, I'm just writing it in a different way so that now I have the same base. So hopefully you recognize that 3 squared is the same as 9, so I have not changed the value, just changing the way I write it. The reason I do that is because now my bases are the same. I have a 3 and I have a 3, so I'm able to set those exponents equal using the property of equality. I'd have 2x equals 20, which gives me x equals 10. And there's C. When I look at D, I'm going to try and, again, I have different bases. I have a base of a 4 and a base of an 8, so I want to make those be the same base. When I look, I'm thinking, well, 4 times 2 is 8. Maybe I could do that. But remember, you'd have to write it as an exponent, and 4 squared is not 8. So I can't use a 4 as my common base. My common base is actually a number that's not up here right now, and that would be a 2. I know 4 is the same as 2 squared, and I'm just going to keep the 2x there. And then when I look at the 8, I know 8 is the same as 2 cubed. So remember, 2 cubed is 8, because it's 2 times 2 times 2, and 2 squared is 4. 2 times 2. So I haven't changed the value. I still have a 4 and an 8 up there. I'm just rewriting it so they now have the same base. So now as I look, I'm going to set my exponents equal. So I would have 2 times 2x equals 3 times the quantity x minus 1. And I go ahead and solve this equation for x. So I distribute the 3 minus 3x from both sides. So I get x equals negative 3. Now I can check this with my original problem. I would have 4 to the 2 times negative 3 equals 8 to the negative 3 minus 1. So I get 4 equals negative 6. 4 to the negative 6 equals 8 to the negative 4. Now you might think that doesn't check, but if you actually plug this in your calculator, and remember when you have a negative exponent it moves it to the denominator, so we'd end up with a fraction here. But you can go on your calculator and take 4 raised to the negative 6th power, and then you would take 8 raised to the negative 4th power, and you should get the same decimal. Mine came up in scientific notation, so I got 0.000244. And I did get that for both of them. So this one does check. I would think right here you might not think those are equal, but you'd have to plug them in to check it out. And then we'll go to E. This one does not have the same base, but hopefully you guys can come up with the same base. What could I make 100 turn into? 10 squared, right? I could rewrite this as 10 squared. So then it'd be times this. So I'd have 4x plus 1, because now they're both a base 10, equals 2 times 3x plus a half. So as I distribute that 2, I would get 6x plus 1. And I'm going to go ahead and solve for x here. Oh, I gotta erase this. Excuse me, my eraser's not working. There we go. All kinds of problems going on right now. Okay, minus 1, minus 1. So I have negative 2x equals 0. So when I divide by negative 2, I would get x to be 0. If I wanted to check that, you could even come up here and just plug a 0 in. 0 times 4 is 0, 0 plus 1 is 1, so I'd have 10 to the first equals 100 to the 0 plus a half, so 100 to the half. And if you check 100 to the half, that is 10. So you would see that that answer checks. In letter F, now I have my first one where I have a fraction as my base. I want to rewrite this 25. I would say it's 5 to the x, and I'm going to rewrite that 25 as 5 squared. And then it'd be to the x plus 3. I'm going to put this in parentheses again. Now, in order to get that exponent out of the denominator, if you remember when we first learned negative exponents, let's just pick one like this. To make that positive, I move it to where it's not. So I would move this one to the denominator. So the same thing applies to if I want to move my 5 squared to the numerator, I would just have to make it a negative exponent. So it'd be 5x equals, and it'd be 5 to the negative 2. And then it'd be times the x plus 3. If you want to double check that, you could always on your calculator put in 1 over 5 squared, so 1 over 25, you get that decimal, and it should be the same decimal as 5 to the negative 2. That's how you'd know that you did that correctly if you weren't sure about it. Now that I've done that, I have the same exponent for both. So I have x equals negative 2 times x plus 3. I'm using my property of equality again, same base. When I distribute that negative 2, I'd add 2x to both sides. So I have 3x equals negative 6. And when I divide by 3, I get x to equal negative 2. And then again, you could check that if you wanted to. The last two then, we're going to have to move all of our fractions out. Now there's a way to leave these as fractions and do them, and if that's something that you just naturally do and you get the same answer as me, don't change it. That's totally fine. I'm going to leave my base as a 3, and I'm going to rewrite this 9 as a 3 squared. So then when I need to move those exponents to the numerator, I know that this would be 3 to the negative 1, and then equals 3 to the negative 2. So I'm moving my 3, my base, from the denominator to the numerator, which is why those exponents became negative. I'm going to go ahead and distribute right from the start here before I set them equal, because I think you're probably at the point where you could do that. So I'd have negative 1x minus 4 equals negative 2x minus 12. I'm going to add 2x to both sides. So x minus 4 equals negative 12. And when I add 4 to both sides, I get x to be negative 8. And again, you can check that answer. Last one, you guys can try if you want. If you want to pause the video and check it out, you can. Otherwise, you can just listen. I have 9 and 27. I know I can't make a 9 turn 27, like 9 squared is 81. That's not going to work. And 27 squared is going to be a big number. So I'm looking for a number smaller than 9 that they both would be able to be like a square of, or a cube, or a fourth. And with 9, hopefully right away you think of 3 squared. So if you're not sure about 27, you should be, because we use this one a lot. But if you're not, you would just say, okay, what's 3 cubed? What's 3 to the 4th? Let's try and make this a base of 3. And hopefully you do realize that 27 is 3 cubed. So to move those to the numerator, I'd have 3 to the negative 2 times 2x plus 5, and 3 to the negative 3 times the x minus 2. Again, I'm going to just distribute right up here, save myself a step. So I have negative 4x minus 10 equals negative 3x plus 6. So we'll solve for x here. And you wouldn't have to show all this work if you do some of this in your head. I get negative 1x equals 16. So x is a negative 16. Hopefully that makes sense for you. You're going to have a worksheet that you do with this. Oh, look at this. There's the assignment. Scary face. A worksheet 10-1 that you're going to get in class tomorrow. And so that's what goes along with this lesson, is worksheet 10-1. Let me know if you have any questions tomorrow.